Hello, my name is İzzet. Today, I try to explain how to solve coin change problem with dynamic programming. First of all, what is the problem? The problem is defined as we have a lot of different unit coins, like this, S1, S2. These are different unit coins. And also, we have amount of money. This is M. If we try to exchange the amount M with these coins, how many different ways we can do? How many combinations are there? Let's look at this example. S is the set of our coins, 1, 3, 5 and 7. M is 8, which is amount of money. So to exchange the amount of money with these different unit coins, the combinations will be these ones. One of combinations is 8 pieces 1. Another case is 3 pieces 1 and 5. All of them here. There are 6 combinations. How can we calculate this number without counting? How can we do using an programming or algorithm? If we use dynamic programming, we should define a recursive function. Let's do this. To construct the recursive function, we have to reduce the problem to subproblems. Ahead, to identify the problems, there are two different situations. In first case, if we cannot use the new coin unit as I plus 1 when we increase the value of iteration I by 1. I is iteration of coins. Let's find the combinations while j is 6 and I is 3. Since I is 3, we have 3 coins, which are S1 is 1, S3 is S2 is 3, S3 is 5. So let's find the combinations. One of the samples is 6 pieces 1. 1, 1, 1, 6 pieces 1. 3 pieces 1 and 3. Another is 1 and 5. Using these samples, let's calculate other combination, that is C4 and 6. If I is 4, we have all coins 1, 3, 5 and 7. We can rewrite the same combinations we found here. There is a different two example. What is different? Different is new coin. This is S4. So we cannot use a new coin S4 because the amount of money is 6 and it is smaller than 7. We cannot use. So we can reach the conclusion C4 and 6 is equals C 3 and 6. To generalize the first case, we can say C, I and J is equals to C, I minus 1 and J when new coin Si is greater than amount J. Let's look at second case example. Find the combinations while J is 8 and I is 2. Since I is 2, our coins is 1 and 3. One of the combinations is, of course, 8 pieces 1. Since I is 2, our coins is 1 and 3. One of the combinations is, of course, 8 pieces 1. Another point is 5 pieces 1 and 3. And 1, 1, 3, 3. Let's calculate. I is 3 and J is 8. I is 3. Our coins are 1, 3, 5. J is 8. So we can use the combinations. Let's write them again. We have a new coin which is 5. You can find new combinations using 5. 3 pieces 1 and 5. 5 and 3. If you formalize the situation, C 3 and 8 equals C 2 and 8 plus what? So how can we calculate this part? This part includes 5 samples. This part includes 3 samples. So this part includes 2 samples. These samples belongs to C 2 and 8. So there are new samples which include 5. Let's calculate C3 and 3. What is the combination of this? 1, 1, 1 and only 3. So number of combinations equals number of these new combinations. Because we can calculate the combination, the samples, adding 5 into them. So we can write here C 3 and 3. If we write the general formula of second case, C I and j equals C I minus 1 and j plus and 3. What's 3? 8 minus 5. So this is j minus 5. 5 is Si. When Si smaller than or equals j. So what happened in this condition? If I is equals to 0. If I equals to 0, that means there is no coin. So there is no coin, there is no combinations. Therefore, these must be 0. What about this? If j is 0 while e is not 0, it should be 1. Why? If we get j equals si, so this is case of j equals 0. If I equals 3 and j equals 5, that means si equals 5, and so si equals j. So c 3 and 5 must be equals c 2 and 5 plus c 3 and 0. Combination of c3 and 5 and c2 and 5 so number of sample here is 3, here 2, so number of sample is here 1, it should be 1. Then C3 and 0 include a sample which is a set without 5. So this must be empty set, because this should be the empty set, so that when we put the new coin which is 5 or S3 in it, we can get a set that consists of only element 5 or S3. In conclusion, these must be 1, because there is a empty set. So let's start to fill the table. To begin with, C11. C11, I is 1, J is 1. Since I is 1, Si, that is to say S1 is 1. So j is equals si. C0, 1 plus C 1, here is all 0. Of them. C0, 1 is 0, C1, 0 is 1. So C1, 1 equals 1. If you use the recursive function, the table is filled like this. Let's calculate the time complexity. Indeed, you can see easily through table. In the table, the number of row 5, which is n plus 1. Number of columns is 9, which is n plus 1. Therefore, the time complexity should be n plus 1 times n plus 1. So, this is equivalent of order of n times n. My presentation is over here. Thanks for watching.